Hey, how are y'all?
How are you?
Good. Y'all ready?
Ready.
Okay. Are there any questions on the homework?
So there's one about like taking area out of the bowl.
Out of it?
Yeah, it was the age of 6.4. Or the last question 6.4, I think. I know, the age of 6.3.
6'3".
Yeah. Yeah, that's the one.
Oh, that was 6'3". That was
All right, so this one is from your homework 6.3, question number 13. So, we've got a hemispherical bowl, half of a circle, half of a sphere, radius 11, filled to a depth of h inches, where h is in between and including 0 and 11. Find the volume of water in the bowl as a function of its depth, h. Check special cases when h equals 0. So when h equals 0, how much volume of the water would you have? 0. And when h equals to 11, you could use geometry. What's the volume of half that sphere? Right. So when it's empty, when it's full, check those special cases. Volume. So thinking about volume, we're thinking about taking something and rotating it around an axis. I suppose there's a couple of ways that maybe you think about orienting the hemisphere in a half circle. So I suppose we could think of the half circle doing something like that, or we could have the half circle sitting on top of the origin. Honestly, it doesn't matter how you orient this thing. The idea is that we're going to take one of these pieces and just rotate it around the y-axis to generate a volume. When we think about, our rectangles, if our rectangles were like this, what method would we be using if we're rotating it around the y-axis? It would be a disk, right? Because if I rotate this rectangle around that axis, I'm generating a circle or a disk. Okay. Same thing here. And you've noticed a lot of times in most instances that we've centered the object at the origin. That's just so we can utilize symmetry and have an easier equation to deal with. You don't have to center it at the origin, right? This thing could be way out here, but then why bother? Because the equation for that is a lot more convoluted than the equation here. So if we orient or structure it in one of two ways, which one of those is easiest to work with, in your opinion, and why? This one, yeah. How come?
Because with the right one, you would have to subtract your formula for the arc.
Yeah.
Your maximum depth.
So we have the center of the circle that's offset. Here, if we orient it in this direction, the center of the circle's at the origin. So you end up with a simpler equation or function. It really doesn't matter if you if you use this, you'll just, that's the point 0.011. So you just have a circle centered at 0.011. Yeah, with a radius of 11. Here we have a circle centered at 0.0 with a radius of 11. Our bounds here would go from here to here. The bounds would go from here to here. So the bounds would also change depending on which situation you're looking at. Again, I would just go with whatever is easiest. This one seems easier to me. It's not that this one's difficult, but in relation, it gets a little bit easier. So we'll forget this situation. Look at this. So now we need to describe the equation of that circle. Circle centered at 0,0. With a radius of 11. So that gives us a full circle. How do we describe the bottom half of the circle? Do we want that? First of all, do we want to solve that for x or y? Yeah, we're solving for x because our rectangles have this thickness. We want everything in terms of y. Y squared. And think of this as like half of the sphere, right? How would we generate this? We would just take this quadrant and rotate it around. So which equation do we need? Positive, negative? Yeah. Well, this is x. What's x over here? Yeah, x over in this region is positive. So we just want the positive root. So we're not really thinking about this part. Right? Once we rotate that around the y-axis, that's going to give us the solid. So radius 11, we know this is negative 11 down here. And we don't, the height we're filling that up to is varying. So I don't know, maybe we just have this water level up to here. We mentioned this previous disk method, pi r squared. Here it's pi times whatever we want to call this function of y squared. So that's our g of y. Sort of volume. Is the integral, pi times the integral of our function g of y, our radius squared.
Is that the root of what?
Well, so this
that's
is
squared, right?
Yeah, we're gonna square it. Right. From where?
I was thinking negative 11.
Negative 11. Yeah, because our rectangles start down here. But remember, we're only going to calculate the volume of water. If we went all the way up from negative 11 to 0, then you're calculating some empty space.
Well, as this, then should it be negative 11 to negative 11 plus the
Yeah, right. Because remember, what we're trying to do is measure this height. If my rectangle starts here at a negative 11, what is this y value right here if we know that distance is h? In other words, once again, we're asked to measure what is this distance if I know this is h. Top minus bottom to measure that always. So we've got h minus 11, top minus bottom. I guess, well, let me do this. What did we say? Sorry. 11 plus h,
Or h minus 11.
or what? Say that again.
H minus 11.
H minus 11. So would that measure that distance? Negative h minus 11. Which one?
Negative 11. Plus
Obviously, how you go together.
Well, yeah, okay. We don't know which one.
Bottom of the y value plus some.
So like if I like if that's negative 11 and I filled the water up to let's say that I don't know. Let's say that has a value of negative 8. What is that? Is what? Yeah. So it's negative, right, this is negative 3 because we're below the axis. We know that's a distance of 3. Yeah? So if we did negative h minus 11, if we did negative h minus 11, would we get 3? If we did h minus 11, would we get 3? So yeah, we would do, no, sorry. We're calling that h. That would give us 3, yeah? What about h plus 11? Here's h plus 11. That work? So then we've got to go back up here and think, well, some of those seem to make sense, but what we're given is that h is a positive number, right? So h is actually, in this context, representing this distance. Yeah, 0 to 11. We wouldn't want that to come out to be negative, just because it's given to us that it's in between 11 and 0. Does that make sense?
Yeah.
Yeah. So which one of those would we use?
Minus 11.
H minus 11? Everybody agree? So in another context, it might make sense to say, well, I can just do, whatever these other ideas that were thrown out. So and notice our bounds, since they are the way they are, when we integrate this, we're going to get a function of y. But when we plug in our bounds, then we get a function of h. Hopefully you can take it from there, but you are going to get a function of h. And then that function of h is what we're after. We're after the volume of the water as a function of h. So given any h, if I fill it up 1 unit or 5 units or 6.37 units, what's the volume of that water? That's what this function of h will calculate. Any other 6.3 questions?
I have a 6.4 question.
Okay. What would say that was 13? Get another one more.
Yeah, it's not too crazy. I just have a question on setting up the cylinder problem.
Okay. What number was that?
That was the last one. I actually have a copy of it here.
Okay. Yeah, it might be slightly different for, because they'll change some of these numbers sometimes.
Right. So I just got confused at the setup of how it's supposed to look like on a graph, because my at least from the notes, my idea was it was going to look like a cylinder, and I was going to be calculating something with a square. But then I don't understand how they got the triangle when it comes to setting up the cylinder.
Oh, because you've got a right circular cone in this one.
See, I didn't understand that. Can you explain that?
Yeah. So,
That's the right cylinder.
yeah, this one's a right circular cone. The one we did in class was for a circular cylinder, right circular cylinder. Here, though, it's a right circular cone.
Okay, I get it now.
Okay.
It's an ice cream cone. I was trying to circle the cylinder the whole time. But,
Okay,
everything
yeah.
you said makes sense.
So why we have this up though? We've got our circular cylinder, and again, it's easiest to center these things like so we can use symmetry. You know, whatever our cylinder is here, right circular cylinder, things like that. So the way we're going to generate that is we're going to generate it taking that line segment and rotating it around the y-axis. But we've got a hole of radius 1 drilled through the axis. So the hole is going to come in here like this, drill out that part. Radius 4 and height 6. So this length is 4 total. We're going to drill out this hole. Radius 1. So it's basically we're taking this line segment, revolving it around the y-axis to do so. I think that problem is, judging on how you print it out, maybe that's a scaffold. It's sort of scaffold.
Yeah.
So the problem is already built in to work through like step by step. But that's kind of what we're dealing with. Once we rotate this, we'll get our cylinder.
Gotcha. Okay. There's a cone.
This is just a line. You've got a means to find the equation of that line. So if there's any other issues with that problem, let me know.
The height of 6, is that as if the cone went all the way to its center point, or is
Yeah.
that the height where it's cut off?
Yeah, so this thing has a height of 6. And we're going to drill through here, so we're just going to assume that this stops at 6, like that. The remainder of this distance will make up for that. So we'll assume that that's 6. Because when we rotate this part, that's going to give us this opening up here like this. So really, you've got 2 points. That's all you need to write the equation of that line. Is this homework 6.4? What was the number? What was it again? 13?
Yeah. That was number. I don't know.
10.
It was the last one.
And number 10. Any other questions on the homework? Where do we leave off? So we left off at 6.5, talking about arc length. Excuse me. Arc length is directly related to the next section in 6.6. 6.6 is pretty short, but it really does build off of the arc length section. So let's remind ourselves, what is the formula for the arc length? Anybody remember it offhand?
Integral from A to B. 1 plus the antiderivative of f of x squared.
Close.
The derivative of f.
Yeah. The f prime squared
F prime squared.
dx. So if you just want to throw all of this stuff in here and work with it as you go, that's fine. If you want to break it up into manageable pieces, also fine. But our first step is we find y prime, because we have to square that, then add 1 to it, then take the square root. So y prime equals what? Yeah. 1/2 derivative of e to the x, derivative of e to the negative x, negative e to the negative x. Then second step is to square. Square both of those. And then just keep in mind that the problems in this section are, unless you're explicitly using technology to solve these, the problems in this section and on the exam will be explicitly designed so that they are perfect squares. Otherwise, we don't have techniques to mess with them, unless it's a u substitution. So in preparation, before we add 1 to the f prime squared, let's go ahead and expand this. E to the x minus e to the x, negative x squared. So we have e to the 2x, we have positive e to the negative 2x. Excuse me. And then we have twice their product. So what's the product of e to the x times negative e to the negative x? Negative 1. Yeah, negative 1 times 2. Okay, so I'm going to close that off. So we've expanded our binomial, then we'll multiply the 1/4 through. Keeping in mind that all of this stuff right here is this right here, which is this quantity squared. Because now when we add 1, just like in that previous problem to this, when we added 1 to this, we get a different factorization of it. So add 1. And then, technically our next step is to take the square root, but maybe we have a 3a, step 3b factor as a perfect square. So what would this look like factored as a perfect square? So if the one with the negative 1/2 here gave us this quantity squared,
This is the positive plus.
yeah, it just turns that into, this is difference squares here in this step. This is now the sum of those squares, right? So this is 1/2 e to the x plus 1/2 e to the negative x squared. Or if, if we looked at it this way, 1/4 times that quantity squared. So just like in that last example, difference of squares, added 1, now it's the sum of squares. So it's kind of like the same pattern repeats, even though the functions look different. Are y'all alright with that? Are there any questions? Okay, fourth step, take the square root. Alright, so that's the entire integrand right there. That's the square root of 1 plus f prime squared. So then we have arc length, the integral of that thing right there. Which one? Yeah, so the 1 got absorbed here. When we squared it, we added 1 to that negative 1/2. So that's where the plus 1 is hiding right there. Our bounds are given to us initially in the problem from negative ln2 to ln2. Do this how you want, but since both of those have a factor of 1/2, I would just take that out front. Put it in later. So now we're thinking antiderivative. It's often, in a couple of sections coming up, when we're taking antiderivatives, we also look at the derivatives just as part of the process. So again, to make sure you're not getting those confused, it's a really easy thing to do. Antiderivative of e to the x, e to the x. Antiderivative of e to the negative x. Yeah, negative e to the negative x. We're evaluating that from negative ln2 to ln2. So f of top e ln2 minus e minus ln2. So upper bound, subtract off lower bound. That evaluated the lower bound. Negative ln2 minus e to the ln2. Up with an exact value for this. E to the ln2 is equal to 2 e minus e to the negative ln2 is 1/2. So again, minus 1/2 minus 2. Sorry, go back to that. So that's the length of this curve right here. At the end of chapter 6, we'll actually look at functions like this. Hyperbolic cosine function is defined as this function here. So we'll look at those. What is it? It's the end of, it used to be the end of chapter 6. It's now in chapter 7.3, but it'll be part of this material. Yeah. All right. So I think that was the last example there. For arc length. Does anyone have any questions on that section? We're going to look at surface area. Again, another application of integration. So your textbook goes through this derivation, which is sort of this portion here. All of this stuff is the derivation and how to get the surface area formula, integral formula. I'm not going to actually use their derivation. If you're interested, then you can look at the textbook and see what they're doing. But the idea is, if we look at this line segment here and revolve that around, so now we're back to revolving something around an axis. This line segment here and here is this line segment. We're going to say, well, what happens if I rotate that tiny little line segment around this axis? I generate what's called a frustum of a cone. So I don't know where that word comes from. Frustum, whatever. So then they derive this based off the area of each one of those. Because again, we're slicing and summing. We'll have infinitely many of these in that sum. So you can go through that derivation if you want. I'll just put here C derivation and text. Start off maybe a more intuitive approach, especially since we've just looked at arc length. Let's start off with just this cylinder. Capital S surface area. So how will we find the surface area of that cylinder? Is what?
Height times.
The base?
Pies.
Which is circumference of the cone.
Cherry pies are square.
Yeah, right. Have you all heard the joke? I'm from the country, so I feel like I can say this without offending country people. But there's an old country couple talking, two guys, and he's saying, "Yeah, I don't know about my son. He's off in college learning some weird things." And he's like, the other guy's like, "What do you mean?" He's like, "Well, they're learning things like pi or squared when everybody knows pi around." So that cherry pie made me think of that. But yeah, so an area is just a length times a length, right? So here, the height is going to give us a length, and the circumference is going to give us another length. Oops. All right, go back to A. This is surface area H times. Yeah, so 2 pi RH is the surface area of a right circular cylinder. Okay, so that idea can be extended to more, I guess, exotic regions, right, via rotation. So let's say we had this function, f of x. We rotated about the x-axis. Get this three-dimensional figure here.
Looks like a board.
It's a gourd. Yeah, totally. So do you think we measure the surface area for that? Yeah. Yeah, that thing. So we're thinking surface area again. It's just a length times a length. When I slice into this, all of my cross sections are generated are circles. So that we'll say that first length is again the circumference of the circle, 2 pi r, and then the length it's sort of extended through, just like this linear length was h. The length we extend that through is the arc length. So that's taking the place, this is taking the place of a linear height. Oh, sorry, it's been sloppy. Whatever. But that's the arc length. The only issue with this is the arc length is a function of x. What's r as a function of x? That's all we need. R as a function of x is given by what? Yeah, f of x. Here again is the radius of each circle defined by the top minus the bottom. So it's just f of x minus 0. So that's what you get on the next page. You get, here's more derivation from your textbook though. The surface area via revolution, 2 pi r, which is f of x minus 0, top minus bottom, times the arc length. That's the surface area formula. So, this is kind of thinking about this as 2 pi r times h in that linear, simplistic example, if you need to. It's only a slight modification to what we were computing in the previous section. All of these problems are constructed so that things work out nicely for you as well. Specifically, this portion where we add 1. When we add 1 to the derivative squared, our derivative squared is typically going to involve a quotient. So it's one thing divided by another thing. So when we add 1 here, we'll see it in these examples, but we're going to add 1 in the form of whatever function we have once we've computed these other operations. We're going to add 1 in that form, like x plus 1 over x plus 1 or something.
Your function, right, is the arc.
Yes, right, exactly. Yep, that's exactly right.
So if it's the arc length, are we just using the outside derivative outside of all of it for the same arc length? This formula for the arc length was the integral, right?
Yeah. So if we just ignore the 2 pi f of x, you have the arc length.
Okay.
computations. We gotta find the derivative, we gotta square it, we gotta add 1 to it. Hopefully we can simplify the radical. But this portion right here, when we multiply the radical by f of x, for examples that f of x is already a radical, that's super convenient because this radical, this y, is this f of x right here. And when we multiply this radical by another radical, things cancel. Especially when we're thinking about 1 in the form of a quotient. So what's going to happen, you'll see in this example, like what we have under the arc length radical is going to be something over 4x plus 6. And then we're going to multiply that by the root of 4x plus 6. So those things will just divide away. And we'll end up with a super easy integral. Okay, so the other thing to point out in this formula is kind of unlike, maybe you've got a method already for disk and shell methods when you have rectangles running this way or this way. With the surface area, the variable of integration is always the same as the axis of revolution. So here, we're rotating this thing about the x-axis, and everything is in terms of x. If we rotate it around the y-axis, everything's in terms of y. Sorry about that. Okay, so we'll just, construct this how you want to construct it, but we're going to go through the steps pretty much the same way we went through the steps with arc length. So we're going to take the derivative. What's the derivative of root 4x plus 6?
2 over square root of 4x plus 6.
Yeah. Yeah. So think about this function as the 1/2 power. So we have the chain rule involved. So that the derivative of the outer, leaving the inner alone, times the derivative of the inner. So 4 over 2 gives us that 2. This to the negative 1/2 gives us this. And then we're going to square that. To 4 over 4x plus 6. Okay, so here's the slight modification when we're doing surface area. Again, when we add 1, we're going to add 1 to this thing here. So we're going to add 1 in the form of 4x plus 6 over 4x plus 6. Does anyone have any questions? Yeah.
Took the added, or sorry, multiplied 4 from chain rule.
Yeah.
Wouldn't it be 8 over root 4x plus 6?
No, well, no, because it's 1/2. Remember, the power comes down, so that 1/2 is there times that 4. All right, so we have our derivative squared, 4 over 4x plus 6. And we're adding 1 to that, 4x plus 6 over 4x plus 6. Now, I know there might be some confusion because we didn't do that with the arc length. I think it's going to be very beneficial to do it this way. The reason we're doing it this way is because we also have the addition of multiplication by the function itself. So we want similar things that we have in the function to show up in the arc length portion, the root 1 plus f prime squared. All right. So we have 4x plus 10 over 4x plus 6. is our 1 plus f prime squared. Now we need to take the square root of all of that. Again, initially that doesn't seem like it's helped us because it's not a perfect square, right? But since this is this portion here, we also have to remember that in the surface area formula, I then have to multiply all of this by the original function itself. Okay, so then we have the surface area is the integral. The function given was the square root of 4x plus 6. Now let's go ahead and just put our 2 pi out here. Times our 1 plus f prime squared portion, which is this. Dx. And we're given 0 to 5 as the balance for this. Okay, so now hopefully this is obvious why we added 1 in that form, because this root out here cancels with this root down here. So that's gone, and we just have a pretty straightforward integral at this point. At least a lot easier than what it was. Have any questions? Yeah.
I don't know if you can show visually or something. I'm just having trouble understanding why in the equation f of x would be the r, and then the equation for arc length would be the h.
Okay, so let's go back to this thing here. So you're okay with that? Like I just take the circumference of the circle, that length, multiply by that length, right? So it's the same idea. I'm going to take this length, 2 pi r, and multiply it by this length. So that's like the h. So it's not straight anymore, so it's not as easy to say, okay, well that's, from 10 to 5 or whatever, right? It's a little more complex because it's curved. We can measure the arc length, and then we have all of these circles extended that length.
So each circle has the same height.
Well, the circles vary, right? So the radius here is different than the circles that radius is here, right? That radius is this radius is that.
I guess what I mean is the h is constant, right?
Yeah, because we say find the surface area from A to B. So once we fix A and B, that gives us a definite arc length. And the radius of each one of these circles, here's another circle, right? The radius of each one of these circles is given from the height of the function down to the axis of revolution. So that's just f of x minus 0. That height radius is f of x minus 0. So yeah, I didn't write that down, but r is top minus bottom, which is f of x minus 0 over f of x. Does that help?
Yep.
Okay. Any other questions? All right, how do we evaluate our integral? then plug the original bound 0 to 5 in, feel free. But if x is 0, then u is 10. And if x is 5, then this is upper bound is 30. You'll always have a simpler function after you've substituted. We have pi over 2, antiderivative of u to the 1/2 is u to the yeah, right, 3/2 divided by 3/2 or times 2/3. Evaluated from 10 to 30. That's a word too. All right, so we have pi over 3. 30 to the 3/2 minus 10 to the 3/2. So I guess, our exact answer, we could write as pi over 3. And then 30 to the 3/2 we could write, I guess if it's simplified, 30 root 30 minus 10 root 10. I guess that's exact. We could factor out a 10, but I don't know what that would do. There's our exact value. And I think, yeah, I did compute that to be about 138.957. So we don't have any units here. What would they be if we did have units?
Square something.
Yeah, square whatever. It's still an area. Square units. That's it. Seem doable? Maybe? Any questions? Pretty straightforward. All right. Let's see. So y'all try that one. sure how far you've gotten, but you should get 15 pi.
I like to think it's right, and it works
So you want to think about it like this right here, like that, and then you can do the.
So I like expanded this one out. Then I made my one numerator right 20x minus 1. And ended up canceling out those two. I just left me at 25. Check my arithmetic on that. I shit. I always want that. I skip the steps. So I got interesting.
25 or 20x?
25 over 20x minus words. So when you expanded your numerator out, your 5 minus 2x.
It's the right side up.
Did you get something like this?
Yes, I did, but if you combine those two terms, combine those two terms, one is 20x, and then those will turn into 2.
But then when you add your 1, 20x minus 4, this 20x will cancel out. This negative 20x. This negative 20x will cancel out. That top term.
I made that 25 minus 1 minus the other one, that's 20.
But
And I
we're
added those two up to 24, just so you're like,
I feel good about this. So I think it's working.
Yep.
if I'm not done what I did then.
Oh, I see. Oh, I gotta be careful.
Yeah, so I mean, we don't have to long with that so far, but at
Yeah, that would probably run into some.
the end you might scratch your head and go, what should I do?
I think that's a good idea. I want to try and keep it like this, and since I multiply this out,
Yeah,
at the end, that would be a little.
I got 2 inches, I just didn't totally bypass that, I got to look like this stuff.
Yeah, and then I don't think it's necessary. Well, actually, because it got me my 25 at the top when I did do that, so I think at the end, I want to pull that more out. Yeah, I mean, that's probably the
So yeah, then you can add form of yeah, so like one is that over that, and then you leave it as
Sorry, you do that.
Well, I want to start this, so I'll just, I don't know if that makes this. So maybe once I'm back here,
Oh, I see. Okay, you just pull that out. That's pretty good. Because then you can pull the 1/4 out of the whole thing. So.
yeah, and then I'm left with.
So does that mean this is over on track with this? So yeah, that whole over is not right. You know, it was close.
root of all of that. Yeah, square root of the top is 5 over 2, 5x minus x squared. We're left with now go back to the formula for surface area. And that's what you're missing. Once you plug it in with the formula, you'll see. So, yeah, 2 pi times, it's the integral of 2 pi r. What is it? What is the radius? R is going to be r. Yes. Yeah. And it leaves you with the integral of 5 halves dx. Yeah. But I'm like, how do I, it's a factor. So it's 5 halves. What's the factor on what's the top? So, yeah, so you square it and you end up
I'd like to just and my life out. And I just
Yes, when you do 4 times that, and you add, which is 4 times that, and then so this is my if you change the 1 into
oh, it's on the two.
x is 4x squared, and then the top, they just drop out the plus 20.
Yeah, it was saying,
I never kind of he doesn't give us well, then you have to actually do the evaluation from right.
You know what? Making this wacky. Yeah. You have the same numbers, they were just it made the adding fun not like yeah, could have gotten there, but it just
Okay, I think I know what I did. So okay, so I have to take and I just 5x. No, I did. Yeah, so top is expanded by the bottom where I ended up. So that would be 5x minus x squared. 5x minus x squared. Now that I have this as my 1 plus, I just take the root of the whole thing. 1 plus was 20x minus 4x squared over 9x plus the expanded out, and that's how I was able to cancel out 20x and 20x 4x, leaving me just the 25 over 20x minus 4x squared. And then I can proceed to the next.
Oh, that makes sense.
When I saw these cancel out, I was going to well, yeah, but we're going to try and use whatever the new denominator is. Yeah.
I was like,
So I put it in that. Basically, this way. Just use a 4 out there. That way it feels land. Before you. Thank you. I was second guessing myself. I understand. Well, I have that.
Clearly, I'll never use it.
Yeah, so that's actually something, yeah. I don't know if it's
I guess if you want to.
Yeah.
I don't know the last time my parents paid for water. Exactly. Because
Well, yeah.
That's what I was kind of worried. I was like,
I'm on the right path.
Well, here's the thing, I finished like that. Teacher never gets right.
Right, did y'all get 25 over 4 times 5x minus x squared for 1 plus f prime squared? Yeah.
It was a long road.
Super tedious, right? And some of you had 20x minus 4x squared on the bottom. That's fine. It's just our next step when we multiply through by f, 2 pi f of x. Maybe it's not totally obvious that you would want to factor that 4 back out. Because remember, we're going to take the square root of all of this stuff and multiply it by the function itself. So if I have the 5x minus the x squared in the square root of 1 plus f prime somewhere, then that's just going to cancel with the function because it's on the bottom, the function's on the top. So let's, I guess, take the square root of that and see. So the square root gives us 5 halves. And some of you did it the other way where you factored out first. That's fine, you ended up with your 5 halves out there anyways. And then we have times the square root of 1 over. Okay, so this right here is our root 1 plus f prime squared. Yeah. And when we multiply all of this by the function, which is the root of 5x minus x squared, f of x is going to cancel with this denominator here. So let's just see that. Surface area, I forget our bounds. I'm going to go from 1 to 4, thank you. We'll put our 2 pi out here. F of x, which is the radii of each circle, times 1 plus f, square root of 1 plus f prime squared, which was our 5 halves, root 1 over 5x minus x squared. Alright, so that root cancels with this root. So we have just 5 halves, sorry, we just have 5 halves dx times our 2 pi, so we really just have this 5 pi times the integral from 1 to 4 of 1 dx, or dx if you want to look at it like that. And so that, if when we integrate that constant, I mean, maybe you can think about it in your head, it's, we're integrating 1 from 1 to 4. So that's just our rectangle, that's a rectangle of length 3, height 1. So that comes out to be 3 times 5 pi gives us 15 pi. Questions on that? All right. The last 2 examples are very similar, so since we're sort of pressed on time, we'll just talk about these briefly, and then we'll move on to 6.7. Is that okay? All right. What time is it? Oh, dang. Sorry. Let's take a break. All right. This example, just to point out that they're asking for, telling you that x and y are measured in meters, but they've given you the fact that you've got a 1.5 millimeter layer of paint. We're just calculating the volume of paint needed, where the volume is equal to the surface area times the thickness. Maybe later on in this course we could look at there's a paradox. You might have heard of it. It's called Gabriel's horn. Has anybody heard of that? It's this figure that's generated revolving around the x-axis on a certain function that has a an infinite infinite surface area but finite volume. Yeah. So you get something that you can fill up but you can't paint.
Is that similar to like the one where you take the cake and you slice it in half infinitely, like amount of times, and then it just stacks on itself infinite amount?
Yeah.
It's the same technique.
I think so. I've never heard about the cake. I've
It's an easy ask.
Okay. Yeah, I've heard. It sounds to me similar to one of Zeno's paradoxes, where he said you can't ever get full way to where you're going, because to get, for me to get to that wall, for instance, I have to walk halfway, and in order to walk halfway, I have to walk a quarter of the way, and in order to walk a quarter of the way, yeah.
That's not necessarily a paradox.
They've labeled it as such, so
It's not a paradox.
we'll go with it. Anyhow, volume, surface area times thickness. So we need to find the surface area of this curve generated from -8 to 8. And so I'll just mention that. And surface area, you should come up with 320 pi. It doesn't say round or anything, so whatever. And then the volume is the surface area times the thickness. So yeah, I think from there it's straightforward, but we'll with 398.36 cubic meters of paint. No. I think I had something else in mind when I did that. It's not right. Oops. So whatever, I don't know, 320 pi times that out. So 1.50, we'll say 1.508. So yeah, this, I did actually convert this. What was it? 1.508. Cubic meters. About 1.508. And I did convert that to gallons just to give us a better sense of how much paint that is. So that's 398.36 gallons. Just to give you a sense of what that volume actually is. I mean, it didn't ask for that, but I think it's more in context of how we think about things. Anyhow, I wanted to point that out. And the last example is the same as what we've been doing. We're just revolving that last example around the y-axis. So just be mindful that when we do surface area, the axis of revolution is the variable of integration. So everything needs to be in terms of y here. They're calling their function p of y. What do I call that? I guess we'll call that p of y squared. P prime of y squared. Py. So that also means when we look at this function, it's y equals to x squared over 4. We need everything in terms of y, so we need to solve that for x and then work with that. So we're finding x prime squared, adding 1, quantity 5 root 5 minus 2 root 2. And that's about 69.968 square units. Sure. In case you are working this kind of as a supplement to your homework. Yeah, so that's pretty much it. Do you have any questions? If you run into any issues, of course, on the homework, we can talk about them. I did want to also mention in homework number 3 and number 5. You have to use technology to integrate tech to integrate. Does anybody know of a good integration calculator online?
Integral-calculator.com.
Integral-calculator.com, yeah.
Wolfram Alpha.
Wolfram Alpha is fairly intuitive. Symbol Lab, does anybody use that? Okay, so I'll just write a couple. I've never used that one actually. I think it's that. I should check. Symbol Lab is really good because it's got all of the symbols there for you, so you can explicitly see what you're actually integrating. Wolfram Alpha might have improved over the years, but I'm not sure. So it has all of these signs. You can just click it and then fill in what you need to integrate. So you just type that out and it'll give you the solution. So I think that one's pretty good. So this one you would just type out. So I would just type out integrate. And then my function. So you would actually just type out function here, whatever it happens to be, and then you can say from whatever your bounds are, 1 to 9, and then it'll calculate it for you. So if you have any issues, let me know. We're going to start 6-7, continue 6-7 on Thursday, and hopefully 7-3 as well. This is really the only application section that we see. All of the other sections where we're looking at techniques, more of a mathematical perspective, those sections you can look at the end of the section in the textbook to get some applications of everything else we do. But as far as just like a section devoted to applications, this is it. We're going to look at 3 types of applications: mass density, work and force, and force and pressure. So we're going to go in that order. So the work and force problems we're looking at deal with springs, and lifting problems. if I've got like a parabolic trough, how much work does it require to lift the water out, or something like that. And then force and pressure is like force on like a dam face. Or some sort of force on some sort of face, whatever. But basically, we're talking about hydrostatic. Hydrostatic pressure as well. I did on D2L, under the announcements, I posted 2 YouTube videos. Once we get to hydrostatic pressure, we'll see that it's actually built in the formula. It doesn't depend on the amount of water behind the dam face. Like if I had all of this water behind the face, or just this much water behind the face, it doesn't affect the pressure on the face of the dam itself. And those 2 videos kind of, one's an experiment that they do, and the other one's kind of an explanation of pressure. So if you're confused, like by the time we get there and talk about it, then I put those videos up for experts to kind of explain a little better than I probably could. Okay, first thing we're looking at is mass and density. In general, mass is density times volume. Primarily in these problems, though, we're not talking about a volume because we're talking about a linear measurement. So we don't have volume. But we could also say that depending on the context, mass is density times area, or we can consider it density times length. So it really depends on the situation. Primarily, we're focusing on density times length. So I don't know, just unit-wise, like if mass was measured in grams, density is grams per cubic meter, let's say, and then volume would be cubic meters. So we see those units dividing out. Same thing with area. We would have mass is grams per square meter, and then the area is square meters, and so forth. Density is abbreviated with the Greek letter rho. So when we see that, that's our density function. Because what we're going to do is we're going to assume that, we don't have a uniform density along like a string, like maybe a guitar string or something really thin. We're going to assume that density varies throughout the string length. But the idea is still the same as we looked at many of those ideas earlier in chapter 6, where we just slice that region up and then we sum all of those things together. So the mass of the kth subinterval, imagine these are really, really tiny slices. We have density rho of x times its length, delta x. So this is density times length. Gives us mass. So we just slice and sum all of that up, which leads us to our infinite sum, which leads us to our integral. So mass from A to B, and A to B is just the length of that bar, or string, or whatever. Density function times its length. We just sum all of that stuff up.
That's rho of x, right?
Yeah, rho of x dx.
So then instead of using volume, you just use the length.
these examples are pretty limited. When you move on to Calc 3, you'll look at more elaborate scenarios. That's when you start using vectors. If y'all have taken physics 1 or 2, you've probably used those. So that's more of a Calc 3 thing. So find the mass of a thin bar with this variable density here. So what would we do with this function in order to find the mass? Yeah, we would have to add them. So then what would the mass look like? Mass function, the mass is the integral from where to where? Right. Yeah, so since it is a piecewise function, it varies in more than one way, I guess. So those problems are pretty straightforward, just like that. There's not much we can do with that. And whatever our units are they given? No. So the mass is whatever, kilograms, whatever, they're given to us. Work and force are a little bit different. We have more applications with work and force. We're going to measure work in joules. So work is joules. Anybody remember the units for joules?
Degrees and grams and something.
Kilograms.
Kilograms per second squared.
Not quite.
Meters.
Yeah. Kilogram meter squared per second squared.
But also units per second squared.
Yeah, newtons per second squared. Yeah. Because our force is measured. This force right here is measured in newtons. Newtons, units, kilograms per. We'll think about, distance is measured in meters, so the units for newtons has to be what?
Kilogram meters per second.
Kilograms, meter per second. That's a times. Okay, so there are joules. There's equals our newtons times our distance. Whatever that is. I'll just keep distance here. Maybe one or two of these will kind of line up. Once we see the formulas, we can line up the units to see if it actually turns out that way. So the idea is that our force varies. Our force is described by this capital F force function. We're pushing this along from A to B. The idea is the same as it was with density, as it was with volume, as it was with surface area. We're gonna slice this region like this, and then we're gonna sum all of that stuff. So we've got a varying force to compute the work done from A to B. We take the force function, and then the dx is just this tiny little distance that force is moved across. So work, force times distance, slice and sum, infinite sum, gives us our integral. guess we kind of look at two different scenarios, I guess. With work, we look at first work done on a spring, like at a base Hooke's law, and then we look at the work it takes to, lift something out of a trough or a reservoir or something like that. So the spring problems, the equilibrium is the natural resting point of the spring. We're going to take that to be x equals to 0. Any compression, x is going off in the negative direction. So if I compress a spring 2 meters, then that's now negative 2. If I compress the spring 2 meters, it's now positive 2. So stretched, positive x, compressed, negative x. That's how we're going to indicate stretching and compression with positive or negative. Do what?
The equilibrium is at x equals 0, right?
Yeah. Right, yep, exactly. Okay. And the examples we're working with, it's the assumption that they obey Hooke's law. Sometimes it's not as straightforward as that, but for us, and then the Hooke's law gives us that the force of that spring is measured by K, where K is the spring constant, and X is just the distance of compression or stretch. But we do have to view this as a function of X. We don't want to put values in for X based off compression or stretching. So if we go back here to this picture, if we think about this as like a spring, then maybe this is our equilibrium here. If I stretch it, then that's going to be part of my bounds. So like that would be from to B for this kx function. So that's how the stretching or compressing gets factored into that, the overall work of that spring. So I'll denote that on the next page, just so we're not confused. But it's the idea. I don't know if I said it. So our bounds work equals to kx dx. And this is where our stretch or compression would go. That's it. Just changed all this stuff. It's weird. Okay. Seems like it's thicker. So this is our stretch compression length here. Stretch compression length here. So that's where those go. Okay, so let's assume a spring constant of 400 kilograms per second squared. Define the work in joules. Required to 1, stretch the spring 10 centimeters beyond equilibrium, and B, compress the spring 2 additional centimeters when it is already compressed 3 centimeters. So joules, those units were what? Yeah. So any glaring red flags in this problem? Yeah. So be super mindful of the units. We want everything in kilograms, meters, but they're giving us stuff in terms of centimeters. Stretch and compression are in terms of centimeters. So you want to be careful right off the bat with those two to convert to meters. So part A. We're given K equals to 400. We can configure units later, but K is 400. So what does the work setup look like then in part A? Okay, so if we're stretching the spring 10 centimeters beyond the equilibrium, it's starting at equilibrium, which is an x value of 0. And then since we're stretching it beyond equilibrium, it's positive. So 10 centimeters, 0.1 meters. So that's how we deal with the stretching and compressing in the bounds. And then what's the function we're integrating? Yeah, 400x. The function we're integrating is kx. We're given k. That's it. That's calculate that. It's the amount of work for that particular spring. So the 400, the units are kilograms per second squared. What are the units for x? Meters. The units of dx? Meters. So we've got kilograms, meters squared per second squared. That's our joule. So you should get 2 joules as the answer. Anybody have any questions on that? Okay. How about part B? The amount of work to compress the spring 2 additional centimeters when it's already compressed 3 centimeters. What would that look like?
2 intervals.
That's our function. We'll say that again, sorry.
Is it 2 intervals?
I probably could. I don't know that we need to, though.
Just 0.02 to 0.03.
Okay, so would it be point? Would it be 0.03 to 0.02? Yeah. Why? Well, yeah. Why 0.05? Right. Yeah. So it's already how much to compress 3 centimeters, but it's already compressed 2 centimeters. So it's already a negative distance, 0.2 centimeters away from the equilibrium.
It's already compressed. The bounce is negative 0.3 and negative.
Yes. Yep. So it's already compressed 3 centimeters, which is 0.3, but it's negative because that's indicating compression. So it's compressed 3 centimeters, and then we want to compress it an additional 2 centimeters. So now we're at negative 0.05. Does that make sense? Yeah. Any questions on that?
Why do you put negative 0.05 on top instead of the bottom since it's the smaller number?
Yeah, so it's kind of weird. But here's our equilibrium point. We're compressing it 3 centimeters. And then we want to know it's already compressed 3 centimeters, but then we want to know what work is required to move that or compress it additional 2 centimeters.
So it becomes that upper down.
Yeah, so it's already here. This is kind of like our new equilibrium. Not really, but that's where it's, holding at. And then we're going to squish it back more. Does that make sense, y'all? Okay. Any other questions? Yeah. The what? The dx, that's the, so this is force. The 400x is the force, and the dx is the tiny little distance it gets moved. So like here's our spring on this axis, let's say. It's a terrible spring, but what we're doing is we're slicing that and summing it. So like just right there, that dx is this distance. So that's what our dx is this little tiny distance there for that one. Okay, that's 0.32 joules. Pretty cool. All right, so let's all think about problem 3 then. So we got a 270-pound person compress the bathroom scale 0.09 inches. If the scale obeys Hooke's law, how much work is done compressing the scale if a 330-pound person stands on it?
Do we have to convert to metric or leave it at inch?
Yeah, leave it. We can leave it at units as pounds per inch or whatever, or inch pounds or whatever it turns out to be. Yeah, don't convert it. It's fine. What do we need to do first here?
We have to find our spring constant.
Right, yep. So remember that we've got to integrate f of x function, the force function rather, which is kx. We need to find that k. That k is constant for this scale and this spring. For the spring and the scale, rather. So how do we find k?
Multiply 270 pounds by 9.8 seconds.
Okay.
It's a negative line.
Yeah.
So are we given a force here? A weight, which is a force. Yeah, weight is a force.
Oh, that's
Weight,
true, yeah.
mass times gravity is weight.
It's also divide. So you divide that number.
So that's a force. So like what we say? Okay, 270 pounds equals to k. We're trying to find k. Then what's this x here? Yeah, this person compresses the scale. That distance, that x. But is that okay how it is? I mean, our spring constant should be positive, right? That's going to give us a positive k. But in actuality, the weight is pushing down, and the scale is being compressed. So, technically it should be negative and negative here. If you like miss that, it's not going to matter because you're still going to get a positive k out. But okay, so k equals what? What is that? 3,000. 3,000. So now we have the constants for that bathroom scale spring. Then what do we do? Do what?
Set up a work problem.
Okay, so we can set up the work problem at this point? Or can we? Work is something times
Find the compression.
3,000 x tx. So this is ultimately what we're after. So, sorry, say that again.
We don't have the compression now.
Right. We're trying to find out how much work is done compressing the scale if a 330-pound person stands on it. So if we have this so far, but we don't know what these bounds are.
Zero.
Wait, what? Sorry.
270 on bottom, 330 top, right?
No, because this isn't a distance that scale spring is being traversed.
Would you plug 330 into f of x and then plug in 3000 for k and then you solve for the x?
Right. Yeah. What was your
Well, let's
suggestion?
say the initial distance on the scale would be 0, right?
Yeah.
So it'd be 0 to something.
Yeah. Right. Yeah. How do we find that something? We have our force function. So this tells us that our force function for any distance stretched or compressed is 3000 x. So let me just state here next to find the bounds. Maybe bound, if you will, to find the bounds. We have to use that force function, the spring, with 330 pound person. Because what we're using that for is we're after the x, we're after the amount of compression on the scale that person is generating. So use the force function with to find x, which is the amount of compression. Does that make sense? We have to have that in our balance. We got again a force, 330 pounds, acting in the downward direction, equals to our spring constant times x, and then we solve for x. So what is x?
Negative 0.11.
Negative 0.11. And that makes sense. It's consistent. Somebody's stepping on the scale. It's getting compressed. Negative value for x. All right. So then we're able to put our bounds in. Work. As was stated earlier, it's the integral from 0 to something. Now we know that something on the same function.
What should be the other way? You're gonna do that? It'd be negative 0.11 on the bottom.
No, because the scale starts at equilibrium, and once that person steps on it, then it's compressed. So start to finish. Starts at equilibrium, then it's compressed.
What would our units be?
So what would our units be for this? Let me write down the answer. 18.15. No, not joules. None. So the 3,000, what are the units associated with the 3,000?
Pounds per inches squared.
The spring constant, it's constant, has no units. I thought I heard it. X, amount of compression, how are we measuring that? Inches, yeah, so X has units inches. And dx, another change in X, small change in X. Another, how much?
Also inches?
Inches. Where are pounds at?
From the question, it's in pounds.
Yeah, our force is in pounds. So I guess this force is actually pounds. So that wouldn't make sense to have inches squared. We'll consider this whole thing together as our force. So that's in pounds. Just because we're talking about people in pounds or pounds inch. Or multiplying. We would say inch pounds, I guess. That's the real thing, isn't it?
Yeah.
I think the word has to be a positive, but
that negative 0.11, is that negative just?
Say that again? Yeah. So so when we integrate this is 1500 x squared from 0 to negative. Force. Any other questions?
Times gravity. Velocity something per second, so it's gravity for that.
Probably won't have a chance to start these problems, but let's, I at least want to show you where the formula comes from. So we have this trough here. We're trying to lift a certain amount of water out. Maybe it's all of it, maybe it's half, whatever. And we're going to use this one. It's more generic. This is the top of the outflow. So the water is in this tank, and here's where it gets pumped out. There's a hose there, whatever. That's the top, the outflow of the water level or liquid level. So we're calculating the work done to lift all of this water out of this vessel. Remember, work was force times distance. Specifically, this is referring to the distance of lift. Once we see the formula, you can just, if you want to remember the formula, that's fine too. But I'm going to show you where the formula comes from. How do we define force? Yeah, that was the units for force. The force was what times what?
Mass times acceleration.
Yeah, mass times acceleration. Acceleration is given by what?
Gravity.
Yeah. Okay, mass times gravity times distance of lift is equal to work. What do we know about mass? How do we define mass? Yeah. So are we talking about a linear, an area, or a volume here? Davis.
Be density times volume.
Yeah, density times volume. We have the density of this liquid we're working out times the volume, right? Because it's in a three-dimensional vessel. So mass is density times volume times gravity times distance of lift. We got one more minute. But when we're looking at a three-dimensional object like this, and we're talking about the cross sections, we don't want to think about the volume of the object. Just like in every other problem we've done, we want to think about the area of the cross sections that are generated here. So we want to take this one step further and say volume is area times thickness. So we have density times area times thickness times gravity times the distance of lift is what's giving us work. And the reason we're breaking it down like that because we have to look at what's given to us in the problem. We're looking at a volume strictly in terms of a two-dimensional thing, in terms of area. So we need the area. The density and gravity are constants. Depending on the liquid, that density is going to be constant, right? Gas, water, whatever. Gravity's constant. Thickness is going to turn into our little dx or our dy. So really we've got to think about, okay, well, what's the area as a function of x or y? And what's this distance of lift as a function of x or y? So we'll pick back up there on Thursday before we look at the formula.
Yes.